Another important concept is that concept of functions. So we're going to be talking about functions here. And the basic functions are power functions, root functions, polynomial functions, rational functions, algebraic functions, trigonometry, exponential functions, logarithmic functions. Now, what we will basically be doing here will only be focusing on the domain and the shapes of these basic functions. The reason for doing the shapes is sometimes you have data. Let's say you have collected some data. To give an example, suppose that you had a patient, or you had some bacteria, and you noticed that as you keep track of time, the bacteria keeps increasing. The number of cells of that particular bacteria is increasing, and now you wanted to model the total number of bacteria cells at a particular time. Like with respect to time, you just want to model that. Now, how will you be able to do that? The first thing is you will have to plot these points one by one. Maybe, let's say after 1 hour, how many cells? After 2 hours, how many cells? After 3 hours, how many cells? And then you keep plotting that. Once you plot that, you will see that they obey a certain shape. If the shape is one of these functions, it will be easy for you to pick one function and say, okay, I want to model this using this power function or root function or polynomial function based on the shape of your plot. And then, of course, it's not gonna be 100% following this, but you can either decide to shrink the function, or you shift the function, or you stretch the function to get the actual model of your phenomenon. So for us, we just want to take the basics, the basic shapes of this, and then when you're plotting, you will see, okay, maybe if I'm using this function, I can model using that. And even when you're creating your code, if you're going to be coding or you're using whatever model you would be using, you can either use Excel, GeoGebra, or any other software of your like. So now, this is the importance of doing these things. The fact of knowing the shapes, it will be easy for you to choose a function to use to model. Now, how are these functions look like and what they actually are mathematically? So let's say now you are looking for the power functions. How do you recognize power functions? This is power functions. Power means exponent. So as long as you have your f of x equal to x, this is the one that is a dumb variable. So this is a variable or independent variable, this x. And then the exponent, I can say a, where a is a constant. A is a constant. So we recognize power functions by just having x, only x. There is no constant in front of x, it's just x. Okay, let me just say it's 1 because there's 1 there. There is 1, and then the exponent is a constant. Now, if I have, let me take some examples here. I have f of x. Okay, instead of f of x, I'm going to use y. You have y is equal to x. You can see that there is a 1 there, and 1 is a constant. So this one is a power function. If you have y is equal to x squared, 2 is a constant, and the base is only x. So this is a power function. Y is equal to x cubed, 3 is a constant, and x is the base. There is nothing in front of it, so this is a power function. And the other power functions can be x to the power 4 and y to the power 5 and so forth. But now, who said that this constant need to be a natural number? A constant can be any number. It can be any real number out there. So suppose now I have y is equal to x to the power 0, which is the same as 1, as long as x is not equal to 0. So if we have that, remember that we have a constant and we have x as a base. X is a base and 0 is a constant. So this one is a basic or a trivial power function. And then you have y is equal to x 0, 2. 0, 2 is a real number. It is a constant. And x is the base. So this is also a power function. Y is equal to x to the power 2 over 3. 3 over 2 is a real number. If 2 over 3 is also a real number, which means it is a constant, and we have x as a base, we have nothing there. So this is a power function. And we can also have y is equal to x to the power minus 1, or y to the power x to the power minus 2, or y equal to x to the power maybe 10 over let's say 11. As long as the exponent there is a number and the base is only x and there is nothing else, we call those functions power functions, right? Now that we got a little bit of the examples and understanding of what a power function is, just a quick recap. As long as the function is of this kind, this is the only base, there's nothing in front, and it has an exponent which is a real number. It can be a fraction, it can be a decimal, it can be a natural number, it can be an integer. It doesn't matter. As long as it is a real number, that function is called a power function. Now, suppose now we group these power functions. Y is equal to x to the power 1, y is equal to x squared, y is equal to x, no, I wanted this to be x cubed, y to the power x to the power 5, y is equal to x to the power 7, and so forth. Now, how is the shape of these functions look like? One thing that we need to agree on here is that if x is equal to 1, this function here is going to be equal to 1. This one here, y will be equal to 1. And if I plug here, I will get y is equal to 1 and there. Because 1 to the power 7 is the same as 1, 1 to the power 5 is the same as 1, and 1 to the power 3 is the same as 1. Now, if you are plotting this, of course, it's always easy to plot the linear function. What is going on here? And this is going this side, and this one is going that side. Now, this one is easy. Everyone knows it. It is a straight line from the origin. So this one is a straight line from the origin, just like this here. So this one is y is equal to x. Now that we have that, how does this one look like? So what we do, we know that at this point here, at some point here, let me not do it here, I want it to be a little bit far. At some point here where x is equal to 1, all these functions are going to be equal. In other words, they are going to intersect there. Now, I pick a value here such that if I plug it here, I get a value. I plug it here, I get a value. So I pick a value that I like to work with. So I'm going to pick a value between 0 and 1. So that value is going to be 1 over a 2, or half. If I plug half here, I will get half, which is something that is here. If I plug in half here, I will get half times half times half, which is the same as 1 over 8. So between half and 1 over 8, which one is bigger? So 1 over 2 is bigger than 1 over 8. So 1 over 8 is supposed to be just somewhere below this function, somewhere here. So this one is supposed to go below this and then go up until it arrives there. Now, when I'm plugging in 2 here, of course, this will be 2 and that one will be 2 to the power 8, which is 8. So it will be bigger than this. So it's gonna go like this. And then this side, of course, is gonna be above and then it goes down like this. Let me do this. So it's gonna be something of this type. And this is y to the power x to the power 3. Again, if I pick a value, I want to check this one and that one there. Of course, this function will be the same somewhere here where x is equal to -1. So they will be the same. Now we want to pick another function between this one and that one. If I were to pick half and I plug it here, I would get 1 over 2 to the power 5, which is, remember that I will get 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2. So I will have 5 of them. So it's going to be 2 times 2 times 2 times 2 times 2. So we have 5 of these things here. So 2 times 2 is 4 times 2, 8, 8 times 2, 16, 16 times 2 is 32. So you have 1 over 32. So 1 over 32 is less than 1 over 8. So 1 over 32. So the value here will be somewhere there. So this function is going to go past there, but it's going to be below, and then it keeps coming, and then it catches there, these functions, and then it comes this way. So this is y to equal to x to the power 5. And of course, this side is going to do the same thing. It's going to be above, and then it catches them there, and then it goes a little bit down. So we can see that the shape of these functions is clear that y is equal to x to the power 7 is going to be below, and catches this, and then it's going to be there. So y is equal to x to the power 7, and then this side is going to go this way, come down, and then supposed to be somewhere there. So this is the shape of these particular things there. And now, how will you find the domain of these functions? You can see all of them are going this particular way. So the domain of this is a set of all the possible input values that you can plug in these functions. So if you have power functions and the exponent is odd, I can plug in the negative things there and I get an answer. I can plug in 0 here and there and there and there, and I still get an answer. I can plug in positive things and I can get an answer. So I can plug in anything. So the domain of these power functions is always gonna be x is an element of real numbers. Those ones with odd exponent. Now, if we group the others, y is equal to x squared, y is equal to x to the power 4, y is equal to x to the power 6, and y is equal to x to the power 8. Right. What are you going to get, or how is the shape going to be? So how do we end up grouping these nice? Okay, we grouped these functions nicely like this, and now we want to see the shape and also the range and domain of this. And also, if you see here, these functions can take all the possible positive outputs and all the positive possible negative outputs. So the range of these things will be y is an element of real numbers. So these ones were done. Let's go for this one. It's easy to plot this, and one thing for sure is that if you really want to plot it, it will look something of this kind. Let me do that, this, that, this, that, that, and that, and we are there and there. So what we're gonna do here is simple. This one is a smiling face, so it goes like this is too much. it's a smiling face. Let me just try and make it normal. Yes, so it looks like this kind. Now this is y is equal to x to the power 2. Okay, let me try and make sure that it looks a little bit cleaner. This one is supposed to be something of this kind, and like something of, I've tried, not bad, something of this kind. Now it's supposed to be like this, yeah, something like this. It's fine, let's work with this one. Now this is y is equal to x squared. What about this? Note that if I plug in 1 here, 1 there, 1 there, 1 there, I get the same value. So here, somewhere here, if I have x is equal to 1, I'll get the same thing. And somewhere there, if I get x is equal to minus 1, I will still get the same value there. So these functions are supposed to intersect at this point and at that point there. Now that you have this nice thing, how do you plot this? Of course, you pick a value somewhere here, which is 1 over 2, and then you plug it there. So you're going to get 1 over 2 times 1 over 2, which is 1 over 4. And if I plug it there, I will get 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2, which is equal to 1 over 2 times 2, 8, times 2, 16, times 2 is 32. So this one here belongs to x squared. This one here belongs to x to the power 4. So this one is less, 1 over 32 is less than 1 over 4. So here we're supposed to get a value somewhere here, which is less than that. Now that we have that, we know that they will intersect at this point, but when I'm picking a value 2, maybe somewhere there, a 2, if I'm plugging in a 2 here, I'll get a 4. If I'm plugging in a 2 here, I will get a 16, and 16 is bigger than a 4. So we expect a value somewhere there. So this function is supposed to go like this, go, and then it catches there, and then it goes somewhere there. And then this one is y is equal to x to the power 4. And if we go with this one and that one, if I'm plugging in 1 over 2 here, I will get 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2, which is the same as 2 times 2, 4 times 2, 8 times 2, 16. This one is 2 times 2, it's supposed to be 4 times 2, 8 times 2 is 16. So this was supposed to be 16, and then this one is going to be 1 over 32. So of course, still the same thing. 1 over 4 is bigger than 1 over 16, which is the same as that. And now here we have 1 over 32. 1 over 32 is less than 1 over a 16. So 1 over 16 is 1 over 32 is always below here. So this function is supposed to go somewhere, go to that point, but when it arrives at 1, it catches this. And if I'm plugging in 2 here, it's going to be, the answer is going to be 32. So 32 is above there. So this function here is supposed to catch this, and then it goes somewhere there. This is y is equal to x to the power 6. So we can expect x to the power 8 to be of this type, and then get others to be of this type, and then they get inside. This is y is equal to x to the power 8. And of course, this side, they do the same thing, and they keep doing the same thing. So this is y is equal to x squared, this is y is equal to x to the power 4, this is y is equal to x to the power 6. So this is how these things look like. One take home for this is that if you have y is equal to x to the power a, and you know that a is 2, 4, 6, 8, 10, it's just an even number, The shape is very simple for the graph. It looks like this. That's what is important. All of them have the same shape that looks like this. Y is equal to x to the power a. And if you look into these functions, I can plug in negative values, I'm going to get something. I can plug in negative values, I can, on all of them, I can get something. And I'm plugging 0 here, is always the answer is a real number, it is defined and it is 0. And I can plug in positive values, there is no problem there, I can plug in anything. Which means that when a is even, the domain is going to be x is the set of real numbers. And now about the range. The range is going to be y is an element of real numbers, such that if you look, all of them, they start at 0 and they go upwards. So they can take any possible output that is above y is equal to 0. So this is greater than or equal to 0. That's going to be the range of these functions. Now, what if we decide to take the fractions? Suppose now we want to look at y is equal to x to the power 1 over 2, y is equal to x to the power 1 over 4, y is equal to x to the power 1 over 6, y is equal to x to the power 1 over 8, and so forth. Or y is equal to x to the power 1 over 3, y is equal to x to the power 1 over 5, y is equal to x to the power 1 over 7, and so forth. How is that gonna look like? How are these functions supposed to look like? Now, notice that I have grouped these together that have a denominator that is even, and we noticed that the shape of these things, how do they look like? Let me draw one. I know the shape of these things. We have just did it. So for this one, we know that if we have y is equal to x cube, for instance, the shape is always going this way and it comes this way. So this is the shape of this curve there. Now, if we interchange x and y here, we will end up having x is equal to y cube. And when we are solving for y here, we'll end up having the cube root of x is equal to y, or y is just equal to x to the power 1 over a 3. Now that you have this, there is a 1 inside. We're using that law that if you have the nth root of a, this is the same as a to the power 1 over n. That's what we did here. Now, interchanging x and y means the inverse. We are rearranging things. What simply this means? It means that we have placed a mirror somewhere there, right? And this mirror of ours, this is the mirror. This is our mirror. Placing this mirror, if you stand in this position, how will you see this in the mirror? If you stand here, you will see that actually this function look like what I'm doing is not correct. Let me remove that. This function will look something like this, and this side is gonna cross and be something of this type. So this one is going to be y is equal to square root x, which is the same as this. So this is how this looks like. You look into the mirror and then you get your nice shape. And you can do the same thing for the 5th root of x or the 7th root of x. One thing for sure, because x cube, we had x cube, we had the same shape, as x to the power 5, the same shape as x to the power 7, which means that the third root of x and the fifth root of x and the seventh root of x, using the same approach, will have the same shape. Now, if I'm plugging in one here, one there, and one there, we're gonna get the same thing, same value. So we're gonna get one here. We're supposed to see this thing intersecting there. And also at -1, this is -1, these functions here are supposed to intersect. So we're trying to draw these functions. If I pick a value somewhere in between, and I say maybe it's 1/4, this is somewhere, this cannot be here. Let me try to be precise. 1/4 is supposed to be here, a quarter. So if I'm plugging here 1/4, I will get 1 over the third root of 4. But we can't really work with that. But it doesn't matter. What matters is 1 over the cube root of 5. These two I want to compare. This one is bigger than this one, which means that if I'm dividing the same thing 1 and 1, the inequality should be going that way. This is small, so I'm dividing this by a small thing, I should get a bigger value. This one is 1 and I'm dividing with a bigger value, I should get a small thing. So this is how this thing goes, which means that if you look into this one belongs to y is equal to belongs to the cube root of x. So if it belongs to that, it means that if I take this and I plug a value in between 0 and 1, the answer that I will get will be somewhere okay. Let me start again. Something happened here, just to make sure that we don't confuse things here. Let me start again a little bit. We have plotted y is equal to cube root of x. Now we want to plot y is equal to the fifth root of x. I am saying that pick a value here. A value is 1/4. Now, if I'm plugging in 1/4 here, I will get 1/4, and then I take the fifth root of that. I will get 1 over the fifth root of 1 divided by the fifth root of 4, and the fifth root of 1 is the same as 1 divided by the fifth root of 4. We have that. And if I am taking 1/4 and I'm plugging it here, I will get 1 over the third root of 4. Now we want to compare these two things. Which one is bigger and which one is smaller? So the cube root of 4 and the fifth root of 4, which one is bigger? This one here, because I'm just taking the third root of 4, but this one goes further and I want the fifth. So this one is supposed to be bigger than that, right? And now that this is the case, I am taking something bigger. I have a 1, I have a 1. I'm taking something bigger and I'm dividing 1. This is big divided by small. The question is, which one will be bigger? 1 divided by something so big is going to be small, and 1 divided by something so small is going to get bigger. So this one is small. Now this side here, which is small, and that they belong to y is equal to the cube root of x, and then this side here, they belong to y is equal to the fifth root of x. Now we wanted to plot that. So this one is bigger according to this inequality, which means that this is bigger. So we are expecting a value that is somewhere. So this graph is supposed to look like this, and it arrives there because they have to intercept. But if I plug in a value that is greater than 1, this is coming down, so it's going to be less. So this is y is equal to the fifth root of x. And then this side also, this is gonna be coming this side and go all the way, hit there, and then it goes that way. And then of course, if I want to plot the other one, let me use this. It's gonna go this way, and then it comes there. Let's try again. It's gonna go this way, and then it's gonna come there like this, and then this one is gonna come down, and then it's gonna come like this. So this is y is equal to the seventh root of x. So this is how these functions look like. Again, the domain for these things is simply x is an element of real numbers, and the range is simply y is an element of real numbers, because they can take on any output of these things. Now, when it comes to, let me look into this, we have y is equal to x to the power 1 over 2. Y is equal, note that this is the same as the square root of x, and y is equal to x to the power 1 over 4, and y is equal to x to the power 1 over 6. Of course, this one looks as if y is equal to the fourth root of x, and this one y is equal to the sixth root of x. So this is how we're gonna do this. Of course, even here we're gonna follow the same principle. First of all, if we were to draw, let me look into this, and if you want to draw this, this is gonna be like this. This is a Cartesian plane, and now let me have an arrow here, because this continues and it goes to infinity, so it's negative infinity, and this to positive infinity, y. Now, if I were to plot x squared simply looks like this, and x to the power 4 also looks the same shape, but they keep moving closer and closer to the y-axis, so this is y is equal to x squared. Now, and suppose I also plot a mirror. I have an orange mirror here. Oh, what am I doing? Let me place this. I also have a mirror here. This is a mirror. This is a mirror. Just write it here. This is a mirror. Now that you have this, we know that if I interchange x and y here, I will get x is equal to y squared, and if I solve this thing here, I will get y is equal to plus or minus the square root of x. Now, this is an inverse of that, which means that this we get it by, so we stand here and we look at the image that we would see on this mirror, which will be on this side. So the image would look something of this kind. So we will have something like this. Thank you. And if we stand here and look at the mirror of what we would get here, you would end up getting something of this kind. Right. So this here, both x and y are positive, right? And its image should also be as such. We know that the square root of anything, as long as it is defined, we always get a positive answer. So this one is supposed to be y is equal to the square root of x, and this one is supposed to be y is equal to minus the square root of x. Why so? This is always going to be positive, and then once we have that minus, so it's always going to be negative. So the only way we can get a negative answer is when the graph is below the x-axis, which is in this case. Now, we wanted to plot this this function here. We do not want to plot it with a minus. So this is not part of this curve here, so we need to remove it. And also, because we got what we wanted here, we don't need this blue thing and orange thing. We don't need that. Let me remove it. We got what we wanted. Now that we have what we wanted, so it would look something of this kind, square root of that. Because x squared had the same shape as x to the power 4, and the same shape as x to the power 6, and the same shape as x to the power 8, then this and that, because these are the inverses of these things, these supposed to have the same shape. We just need to know that when x is equal to 1, these things, they meet, right? So that's what's going to happen. If I pick a value somewhere there, of course, this is still the same scenario. You're going to get this kind of a thing, and this is y is equal to the fourth root of x, and then this one is gonna go there, and then it comes just like this. So this one is going to be y is equal to the sixth root of x. So this is how these things usually work. And when you're interchanging the x and y, the domain and the range, they change. The domain of these things was x is an element of real numbers, and the range of these things was x was greater than or equal to 0. But in this case, we found out that when we are including that side, whereby we would end up having all the possible output values, what we are getting is not a function because of this plus or minus. We don't want input value to have too many outputs. We want it to have one output. So in that case, we end up having only a slice of the original domain as the range for this one. So the domain of this is going to be x is greater than or equal to 0, and the range of this thing is going to be y is greater than or equal to 0. Again, when interchanging x and y, the domain and range is supposed to interchange. But in this case, when we have these nice things, we end up having too many outputs. In other words, the inverse is not a function because it has two values if you place a vertical line test. So we end up restricting our outputs. And then the negative side, we say we don't want the negative side. We just want to focus on the positive side. Hence, our range is not x, is not y as an element of real numbers. It's only the piece of our previous domain. Now, we have tried to plot these things, and we have talked about power functions, and we said that the power functions are functions of this type. We have y is equal to x to the power a, where this is a real number, this is a base, which means that if you have y is equal to 2 to the power x, this is something else because 2 is not the same as x. We want x to be the base. Here we have 2, so this is not a power function. Right. And now, what I want to mention is the root functions. What are the root functions? Root functions we have dealt with just in a moment. So as long as we have y is equal to x to the power 1 over 2, y is equal to x to the power 1 over 3, y is equal to x to the power 1 over 4, y is equal to x to the power 1 over 5, and so forth. You can see that is 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. These are root functions. So what we were drawing lately, these are root functions, and these are also root functions. So we have these are power functions, and inside the power functions, if the exponent is 1 over 2, 1 over 5, 1 over 3, and 1 over 4, then root functions are contained inside. Root functions are contained inside power functions. And that's what root functions are all about. Now, what are polynomials? Polynomial functions. And of course, I'm going to give some examples here. If you have a function p of x, and we have this function is written in this format: a0 plus a1x plus a2x squared plus a3x cube plus a4x to the power 4 plus blah 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 up until you arrive to some n there. We don't know what n is. So if you have a function that is written in this format, then we say it is a polynomial. Let me give an example. If you have f of x is equal to 1, let's start there, right? By setting this one equal to 0, a1, and this equal to 0, and that equal to 0, and that equal to 0, and that equal to 0, this whole part goes to becomes 0, because 0 times anything becomes 0. So this becomes a 0. And now this one you set it equal to 1. So this one here is a polynomial. It's a polynomial. So we have this polynomial here. So this is a polynomial. Now let's try something else and see. I want us to see different examples of polynomials. So if I set this equal to 2, this equal to 0, this equal to 0, this equal to 0, this equal to 0, this is equal to 0, you have f of x is equal to 2. This is also a polynomial. If I set this equal to 0, this equal to 0, this equal to 0, this equal to 0, this is equal to 0, and we left with that, all this part will be 0 and we'll be left with that part. I set this equal to 5. So if I have f of x is equal to 5x, let me just place a 10 there. So this is also a polynomial. Now, if I have f of x is equal to 1 plus x, this is a polynomial, because if you look at these numbers here, you have 1, 2, 3, 4, 5. As long as these exponents here are natural numbers, then we have a polynomial. So here we have a 1. This is 1, which means a0 is equal to 1. This one is equal to 1, and this is equal to 0, this is equal to 0, this is equal to 0, and all the others are equal to 0. So this one is also a polynomial. Right. And if you have f of x is equal to 2x squared plus 3x plus a 1, we got it by setting a 0 equal to 1, a 1 is equal to 3, and then a 2 equal to 2. And all the others became 0. So this one also is a polynomial. So how do we actually look at this polynomial thing? So as long as we have some function f of x equal to some real number, we have some real number here, right? And then here you have x to the exponent. This exponent here is a natural number. It's a natural number. Plus, as long as here you have a real number, x to a natural number plus a number, a real number. A real number can be 0.5, it can be -1, it can be 2, it can be 2 over 3. It can be, as long as here we have a real number, which is a constant, and here we have counting numbers 1, 2, 3, 4, 5. Same thing here, you are adding these things up, then we have a polynomial. Let me give some examples. If let's say we have f of x and f of x is equal to, let's say 0.5 x to the power 7. This is a polynomial because this is a real number and this is a natural number. And if you have f of x is equal to 3x squared plus 3 times square root x plus 2, this one we said this is a polynomial. But here, remember, if you look into this, this does not obey this. We have a real number, we have x, and we have a natural number. Even if, let's say, you decide to say, okay, I have x squared plus 3 times x to the power 1 over 2 plus a 1. This one is a fraction here. It's not a natural number. So this one is not a polynomial. We want our polynomial to be an addition of things like this. This one is a real number, x. This is a natural number plus real number, x, natural number plus real number, x, natural number plus something like that, right? Even in the case of having f of x is equal to 10, for instance. If you look into this, this is equal to 10 x to the power 0. X to the power 0 is 1, so this is just 10. So this one is a polynomial, so this is a polynomial. So this is how you look at polynomials. Now that we looked into this, when we are talking about this if you have, let's say, we have here polynomials, or let me just say polynomial functions, or just polynomials. Quadratic functions are contained inside polynomial functions. Cubic are contained inside polynomial functions. Linear is contained inside polynomial functions. But I know that some instructors try to isolate this, that this is not, it's monomial, blah, blah, blah. But this is a polynomial according to the definition of a polynomial, that any function obeying this, it is a polynomial. It's not poly, means many as in English. This is just the definition of a polynomial. As long as it obeys this, then it is a polynomial. Now that we have got polynomials out of the place, we want to talk about rational functions. What is a rational function? A rational function is very simple. R of x. As long as you have polynomial function divided by polynomial function. Rational function is a function that is a fraction whereby the numerator is a polynomial function and the denominator is a polynomial function. Simple as that. Just the division. Examples of this: if I'm saying I have f of x is equal to 2x squared plus 3x plus 1 all over x plus 1. This is a polynomial, that is a polynomial, so this is a rational function. Right, rational function. And if you look at f of x is equal to 3x cubed plus 2x, or let me just say plus 2. Take note of this. This is the same as 3x cubed plus 2 divided by 1. 1 is a polynomial. Remember that 1 is the same as 1, which is a real number, times x, which is x, to the exponent 0, right? So this is also one of the things that we can say this is 0 and this. So this is a polynomial. Remember that x to the power 0, when I said that I wanted this to be a natural number, I was excluding this because this one here, this is a constant multiplied by x to the power 0. So these natural numbers I was referring on 1, 2, 3, 4, 5, and so forth. But 0 is also part of this, hence I'm including it here. So this is a polynomial, and this is also a polynomial. So this is a rational function. Right. If you have f of x is equal to square root of 3x cubed plus 2x plus 1 all over 6x squared plus 2x plus 7. The denominator is a polynomial. What is inside the root is a polynomial, but now we have a root. This numerator here as a whole is not a polynomial, because a polynomial doesn't have a root. It's not a polynomial. And then the denominator there is a polynomial, fine. So because it's not a polynomial divided by polynomial, this function here is not a rational function. It is not a rational function, this one, because it has a root. Rational function is a polynomial divided by polynomial. And this one we have a root. So as long as we have a root, it is not a rational function. Now, picture-wise, here you have rational functions. So inside here, you will end up having polynomials. Polynomials are inside the rational functions, and if you look at our hyperbola, let's say hyperbolic functions, 1 over x or 1 over x squared, they fall under rational functions. So rational functions are bigger, and then these are just subsets of rational functions. And then now let's go to the final type of functions, and then we can stop there. We talked about having a polynomial divided by another polynomial. So we said that these are rational functions. Now once I include a root, it's no longer rational function, which means we need more type of functions to actually give us a more general class of functions that actually include everything, including taking the square root or adding two polynomials, or dividing two polynomials, and multiplying two polynomials, and all these kind of things. Now that's when we start to talk about algebraic functions. What are algebraic functions? Algebraic functions. What are algebraic functions? If you have a function f, and the function f is formed by multiplying two polynomials, or three polynomials, or four polynomials, by multiplying polynomials, or by dividing polynomials, or by adding polynomials, or by separating polynomials, or by taking a root of polynomials, or it is formed by a mix of these things, that function is called algebraic function, right? As long as you can spot it. Now, if I have the square root of 6x squared plus 2x plus 1 over I'm trying to use this. Okay, it's fine. Let me take a different example. So I have 2x squared plus 3x plus a 1. This here is a polynomial, so we have a polynomial here. And then this thing inside the root is a polynomial. So I have taken a polynomial, I took a root, the root is allowed, and then I have division is allowed, and then I got this. So this function here is called an algebraic function. So this one is an algebraic function. Another one will be, I have x squared plus 1, and then I have x cubed plus 2x plus 3x, and then I can divide this whole thing by the root of 7x to the power 10 plus 2x plus 1. Now, this is a polynomial. This is a polynomial. They are multiplied. Multiplication is allowed. And this inside the root is a polynomial. I have taken the root. A root is allowed. I have divided these two things. Division is allowed. So this one is algebraic function. Right. After we've talked about algebraic functions, the first thing that we also have to look at is the most important thing here. Can you spot the polynomial inside? Suppose I'm having this nice thing here, and then I have the square root of 2x squared plus a 1. Now this becomes interesting. And then I want to multiply here x squared plus 1, and then I want a root of the root of x plus 2x squared. I have this nice thing here. All you have to realize here to determine if is this an algebraic function. First of all, this one here is a polynomial. This one here is a polynomial. Okay. This one inside here is a polynomial. This one here is a polynomial. This one inside here is a polynomial. This one here is a polynomial. So I have a polynomial and then I take the root of it. Root is allowed. I add another polynomial. Addition is allowed. I take the root, which is allowed, plus a polynomial. Addition is allowed. I take the root of that, which is allowed, and then I divide. Division is allowed. I have a polynomial multiplied by, multiplication is allowed. I have a root. Root is allowed. I have a root. Root is allowed. And then I have an x plus 2x squared, which is a polynomial. So this one is algebraic function. Now that we have talked about this, what about this? Suppose now I have the square root of 2x squared plus 3x plus the square root of 2 to the power x divided by 6x squared plus 3x plus 7. Now, this one is a polynomial. Fine. Division is allowed. The root is allowed. This one is a polynomial. Addition is allowed. This is a polynomial. Root is allowed. But this thing here is not a polynomial. So this one is not algebraic function. It's not algebraic function. So that's how you spot it. There must be polynomials everywhere. Roots, division, multiplication is fine as long as we're having these 4 binary operations and the root we're operating on polynomials. We don't want anything that is not a polynomial. So now that we have that, we have algebraic functions. So if you have algebraic functions, power functions are inside, polynomials are inside, rational functions are inside, rooting functions are inside here. So of course root functions are inside, and all the listed above, they are inside here. Quadratic are inside, linear are inside, constants are inside. So algebraic is more powerful. Any function that is not algebraic, we say that function is a transcendental function. Now, when we are talking about transcendental functions, we usually trying to talk about trigonometric functions, we're trying to talk about exponential functions, we're trying to talk about logarithmic functions. So this side here will be the side of transcendental functions, and then this side here, algebraic functions. So that's how we differentiate these functions. And now just a quick example of how you would look at this thing here. Suppose that we wanted to see how this can be used in real world example. I'm supposing that you have some data here. The data is time and total number of bacteria cells, and you want to see if how can you model this using the understanding of the functions. Of course, the first thing that you're gonna do, if you don't, of course, this is a basic problem. You don't have to program anything here, so you can just say GeoGebra Classic. And then once you get it there, you can do this, and then you go to this little triangle there, and then 3 dots, and you're going for the spreadsheet because that's what we want. The spreadsheet, once you have that nice thing there, you can punch in some numbers. The first column was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we had this 1, 2, 3, 4, 5, 10, and then on the other side we had 10, 10, 11, 12, 15, 25, 50, 120, 308, 320, 2213. Now that you have these things, of course, since you want to model and get a function out of these things, or you want to get a proper estimate, remember that this was time in hours. Of course, you have to sleep. You cannot keep recording these things. Suppose you collected this data for 1 day, and now you wanted to see what will be the number of bacteria cells maybe after 20 days or 30 days. Of course, to do that, you need to have a function. So you choose this thing here that has a histogram, and then of course we have 2 variables here, so you can have your 2 variables. And now that you have these points here, out of the functions that we have tried to look at, which one looks like it? And then you look, okay, I've started some of these functions, and then you go here and you choose that model. Of course, this is not linear, so the line of best fit is going to go cut there. It's neglecting this, it's neglecting that, it's only sensing these 3 points. And now you say linear is not gonna be a good model, so you go to a logarithmic function. You can see logarithmic function cannot even do anything. And then you try a polynomial. A polynomial is trying to pick something, but it's losing these 2 points. That one is out, these ones are out. It's still trying, but it's not getting this whole thing. Now you try a different model. Power, it's not doing anything. Exponential looks good, which means that all you just need to have a constant and a little bit try and shrink this function to come this way and move it a little bit back, and then you'll be able to get something. So in your model, you can try and use an exponential function, but have that constant that is going to shrink it a little bit. And on another side, you can try and see growth. Growth is not doing anything. Sine is not doing anything. A sine function. Remember, sine function and a cos function, they usually perform the same way. But a logistic equation, let me say a logistic function, it is actually predicting these points very well. So you can use a logistic, but if let's say you don't know much about logistic, we can still use exponential, because exponential was looking pretty well. We just needed to know, okay, the shape looks like that of an exponential, and then we add a constant, and then in front of this constant we say we have an unknown, and then we try and see if the function that we can get cannot actually predict these points well. But in this particular example, logistic is actually doing pretty well for this. I think we're gonna stop there.